This is Cameron Chai from azom.com, bringing to you another episode of azom.com TV. Today I'm speaking to Ben Garland from Zeta Instruments, and he's going to tell us about their Zeta 20 optical profilometer.
Great, thanks Cameron. This is our Zeta instrument. This is one of several series that we have. It's an optical profiler. Essentially what it is a microscope system, but in addition to that it actually builds up 3D images so that we can measure X and Y dimensions. In addition to that, Z dimensions, so we can measure heights in terms of step heights, angles, and also roughness. On the system we have an optical base plate in which one can put their own sample holder or stage. This is one of our standard stages, which is an XY manual stage with a rotation capability on the top. We have our standard objectives, which cover a range of 5x up to 100x. We have our technology that allows us to enhance the image and the resolution in the Z direction over that of a standard microscope system. Our camera coupler combination, in which are very adjustable and user changeable to adjust to particular sampling needs by the customer. This is a mechanical drive in which we actually take image slices which are based on full field of view of the current camera coupler to the sample. We use high brightness LED for illumination of the actual sample, so the color that we get back is the reflected light of the sample coming to the system, and then we take those slices in the Z direction to build up a 2D or infinite focus composite image, and then we have the 3D information. To actually collect the data, it's very straightforward. If I walk over to the system, this is currently a semiconductor material, so this is silicon that's been etched. It has features, it also has some AR coatings and a variety of other films present. This is a nice sample to illustrate the technology. This is using different magnification lenses. One can actually see the effect in the field of view, but more importantly, the depth of focus. And that changes with the numerical aperture of the actual objective that's being used. If I go to even higher magnification, one can easily see, as I adjust the focus, there are many planes, or there's a huge depth of focus over the sample Z range. What I'm going to do is show you how we can collect this image in less than a minute and build up the 3D. Typically we adjust our illumination control, which is done here, or I can hit auto. The next step is to set the ranges, but what I'll do is actually turn on one of our proprietary capabilities which allows us to enhance this, and that is our focused assist. It allows me to easily see which plane is in focus, so the region in the center is actually our highest point. To set the Z range, I want to scan through the top through the bottom, so I'll simply set top, and then I'll scan to the lowest point. Might actually give us a little more intensity for the contrast, and then scan to the lowest features, set bottom, maybe increase this a bit. So we're going to scan a range of roughly 14 microns, and then based on our 200 slices that I currently have set, our resolution is going to be 70 nanometers per step. What I do is simply hit scan. At any point I can actually hit escape in the data collect if I really didn't want to run that particular spot. You can actually see the image slice that we're taking on the sample. As we actually move the stage in the Z direction, we actually take that full field of view image at each location. At the end, we'll have the results, which will give me a profile across on the upper left. I'll have the 2D infinite focus image here. I'll have a 3D image located here, and the actual numeric values associated based on the cursors. Just like that, we actually have our image. I can now in the software very easily come over and measure steps. So for example, depending on where I put this particular cursor, I can actually look at step heights by taking averages or use markers and measure individuals. You can actually see on the 2D composite where I'm actually located on the actual image. So this cursor pair average height from scan is 10 microns. The average height of the second cursor pair is at 3. Most importantly, if I wanted to know this particular feature, which can be any sample type, I would be measuring a step down, in this case minus 7.8 microns. So it's an optical profiler. I can move these cursors anywhere I want on the screen. I can make them oblique, move them across. I can have multiple cursors on the system. If this were a sample and I wanted to measure roughness, it's as simple as coming up and clicking roughness. Now I actually have roughness values such as your average roughness, the RMS, peak to valley, peak, valley, and then some of the statistical information about the shape and the distribution. Likewise, I can actually measure these as box step heights or box roughness. So for example, if I was interested in these particular regions, depending on where I put the boxes, I would actually have average values for everything contained within a box. The system lets you very easily collect the data, save the data, export the data out. So it's efficient in terms of its ease of use and operation. There's a lot of other capabilities that are available in the system, and if you have more interest, I would recommend contacting us directly. We'd be happy to run your samples and show you feasibility.
All right, Ben, just out of interest, what sort of people you typically use these sorts of instruments?
Essentially anyone that's trying to characterize a surface and measure the roughness, the texture properties. So solar industry, we're very interested in, for example, if they're working with crystalline, looking at the pyramids, measuring the roughness as well as the AR coatings that are present, or the metal fingers. Microfluidics, looking in transparent materials. We have the capability of looking at multi-layers, so I can actually look from a top layer down to a middle layer, all the way to a bottom layer in a transmissive type material and measure those heights. Across the board, there's a whole variety of applications.
That's biological substrates, things like that?
Biologicals, we can look at the morphology as long as it's within the spatial resolution, which is about 0.4 microns for X and Y based on white light. If it's fluorescence, we are not in the fluorescence market.
All right, and what's the maximum sort of Z resolution that you have?
We can step at 15 nanometers.
All right, and if anybody wants more information, they can also go to your website, presumably?
Most definitely.
And what's your web address?
It's www.zeta-inst.com.
All right, Ben, thanks very much for telling us about the Zeta 20.
Thank you very much.